Good morning to everybody. I presume most of you are connected remotely. The room here is not really full, but it's understandable. This session concerns freshwater, saline water interactions and new techniques, or relatively new techniques, to monitor these phenomena. And the phenomena are particularly relevant in many areas of the world where overexploitation of groundwater has caused significant invasion of seawater into the mainland, just jeopardizing the availability of freshwater resources. And coastal areas tend to be overpopulated, as you probably know. So freshwater availability in these areas is particularly critical. So there is nearly a perfect thunderstorm that is involving overexploitation of groundwater, changes in land use, and maybe also climatic changes that is converging towards making this problem more and more critical for the near future. This is pretty evident in the Mediterranean basin, where particularly in the southern part, of course, freshwater resources are very scarce, and in most cases, people use fossil water, so water that has been there for thousands of years, and they basically lower in the water table by meters and meters per year. Okay, so for the future, we don't know what's going to happen. The session has 3 speakers. One is myself, but I will speak last. And then we have Professor Ralf Ludwig from, hi Ralf, from Munich, and then Professor David Lagomasino from East Carolina University. They will introduce themselves better than I introduce them. And Ralf has been so kind to also provide a wrap-up kind of presentation for the entire session. So he will start and he will end this session. And then in the middle, David and myself will talk about more specific techniques, while Ralf will provide the more general view. So maybe, Ralf, if you're ready to start.
Yes, good morning, everyone. I hope that you can hear me. Thank you, Giorgio, for this very nice introduction and stepping into this interesting session on freshwater seawater dynamics in coastal zones, advancing science and technology for sustainable management. So in preparing this session, Giorgio Cassiani, David Lagomasino, and myself, we came together to decide that we would like to open this very important topic to a more general discussion. And please allow me to introduce a little bit into the topics and why we wanted to have this as a contribution to this nice conference. So as Giorgio already mentioned in the introduction, the preservation of water resources in coastal areas is massively important, especially in times of global change or climate change. We see that the natural balance of coastal areas has long been deteriorated, and there's a huge threat that this is going to continue in a substantial way. A number of components that can be listed. It's not an exhaustive list, but if we look at the measurable sea level rise and the projections that we have available, if we look at the very dense population in coastal zones alongside the urban sprawl that is continuing also at a very high pace, increasing the demand for water, and obviously not only the demand, but necessarily also the consumption for different sectors like the industries. If we look at tourism alone, you know that in such areas, the water consumption that is associated to touristic activities is tremendous. Just think of a golf course somewhere in the southern European domain. So we are facing key issues, and those key issues are related to the overexploitation of freshwater resources, particularly in arid and semi-arid areas, to which most of example the Mediterranean belongs, but we can also see results from other parts of the globe where this is just as evident. So if we look at those key issues, we see that the intensive use of water resources may lead to water scarcity. There's several definitions out there, not necessarily quote them right now, but water scarcity can have very high or strong consequences also on the economic development, also on human health. So this is one of our major concerns here. We see the severe pressures on the aquifers and the surface waters that are rising. We have adverse effects on the water quantity, but also the water quality. So we find great evidence for excess nutrients, for increasing pollution, having also effects on aquatic ecology, on biodiversity. And as Georgia mentioned, in particular, in times where we see freshwater aquifers sinking in their altitude, but at the same time the sea level is rising, there must be a tremendous effect on the freshwater-seawater interface. So saltwater intrusions with many consequences that we can see from the contamination of aquifers for other purposes of use, just as much as ground instabilities that can even lead to the collapse of buildings, as we can see unfortunately in many facets in the Nile Delta, for instance. So if we want to manage these issues in a more appropriate way, we have to improve or try to improve our understanding of the dynamics of such systems. So this is also why we have decided to start this session. We would like to make a contribution to bridge the gap between the technological and the scientific development on one side, and the needs for practical management of coastal aquifer systems on the other side. And there's an observation that we can see, while on the one side, in the recent years or decades even, there was a very strong advance in our possibilities to monitor and to describe the interface of that surface-subsurface system. And while we can see that many of these techniques are now state-of-the-art in science or research applications, there is often still not the same level of understanding by practitioners and users to apply such techniques or to use the results of such techniques for their management of coastal aquifers. So this roundtable will contain 3 scientific interventions. I will start with the first one that will generate a more broad vision of the climatic and land use impact on water resources. As myself, I'm a hydrologist, surface hydrologist, in fact, and my main focus is looking into the climate and land use change impacts on water resources. I will highlight this part. Then we will move on to the second part presented by David on new methods in proximal and remote sensing techniques. And then Georgia will wrap up and provide a profound vision on the geophysical methods that are currently available. And then we hope that participants would be willing to discuss with us a little bit on a broader view towards water resources management in coastal zones and policy making in these regions. So I would like to jump into the topic by one figure that I found last night, actually, that was published last year. This is an article on the Mekong Delta, but I think it summarizes quite nicely the impacts that we have. So if we look at the threats to coastal aquifers, you see there's actually a lot of impacting factors. And for me as a surface hydrologist, I have to state But the problem is not only starting at the coastal zone, but as soon as we look into surface or into river basin management, it is evident and obvious that all the processes within a catchment are relevant to what happens at the mouth of this catchment once it reaches the ocean or the sea. And so we see here, while we see sea level rise on the one side, we have the increasing population density and the urban sprawl. I hope you can see that pointer now. We have economic developments along the rivers. We have maybe upstream dams that are controlling the inflow. And one example that I will show in a second will reveal that, hopefully. And we see land use change near the coastal areas where maybe lots of water is needed to irrigate, to support drinking water facilities, to support the cities and also the rural areas with high quality water. So if we tap enough water from the near coast groundwater aquifers, and at the same time we have sea level rise, then saline groundwater can intrude into the existing aquifers and deteriorate the quality of these, and maybe even making them unusable for any type of future activity. So I would like to start with the modeling of climatic and land use impacts on water resources. And I'll jump right into one example. I would like to do this using a case study. And this case study is the Ebro River that I'm sure that many of listeners will know. You can see here to the left side. Oops. So you see the Ebro here located in Spain near the French border. And what you see on this figure, it's actually a local irrigation plan that is part of the river basin management plan. And you can see in those dark green colors that these are the areas where there's new irrigation systems being planned. And you can see that they also advance quite close to the coastline. So the overall plan seems to be that we want to use more freshwater in the future to irrigate for agricultural purposes. And at the same time, we can look at climatic change, for instance, and this is a mid-century vision that is composed of a broad set of available climate model data. And you see that the precipitation is likely to decrease in the range of 10 to 20%, maybe as compared to a reference period of these times right now. And so we have a reduction in water availability. So very obviously, there's a contrast, increase in water demand and reduction in water availability. And so if this river basin management plan is carried out accordingly, then water scarcity in the region will aggravate. It's undoubtedly so. So that must be considered in making future plans for water management in the region. So if we move on, we did this study not only for the Ebro, but we, just to highlight this in some other European or Southern European catchments, a study that was done in the Global Aqua project. You see to the left again the Ebro, and you see temperature is increasing and precipitation, evapotranspiration, and runoff are all decreasing. So that means we're creating a certain kind of pressure on water resources here. And there's another site, if we move to the right here, that's the Ebrotas. It's also a river basin that reaches the coastline, Mediterranean coastline. And you see that the system basically looks the same. We have increasing temperature. And while we have increasing temperature, still evapotranspiration is reduced just because of the scarcity of water resources here. So that means the rivers that will eventually lead into the Mediterranean Sea will be more stressed than they currently are already. And that has large-scale implications for the management of those coastal regions here. What I would like to highlight also, it's not only the role of climatic change, but it's also the role of land use change. And this might take a second to digest this figure. So this is a study we did in the Global Aqua project, and you see on the left side and on the right side, two different types of scenarios. And if you look very closely, you see that there are slight changes that are happening over time. So if you see here, starts in 1990, then in 2000, 2010, 2020, and so forth, until it reaches mid-century. So, and if you look at this from a or often enough, you see that there is change taking place in land use. But the problem is less the land use, it is more the way that the system is being managed. And myopic, so the short-sighted vision, that is a scenario that puts economy first. Sustainable vision practically explains itself. It's a scenario where sustainability is at stake. So we can use these types of land use information. Also, if we move close to the coastal region, for instance, to see how water use is changing. And I would like to highlight this very briefly. So if we look at a sustainable scenario, and if we look into the year 2050, you see what is scaled here, the water demand in millimeters per year. And I flip over to the myopic scenario, and you can see, I'm going back and I'm going forth. You see there's a tremendous difference in the water demand in that basin, depending alone on the way that land use and water resources are being managed. So once again, the sustainable scenario, then the myopic scenario. And so we have a number of contrasting and conflict increasing developments that we are foreseeing for the near future, and that also has a strong impact on the coastal zone. If I move on and show an example of how such climate and land use changes are impacting aquatic ecosystems and even biodiversity, was a study we made only published last year, where we're looking at different species of snails. So the Melanopsis tricarinata, which is a endemic species to the lower Ebro system, versus the Pomacea maculata, or apple snail here in red, which is an invasive species. And monitoring evidences that there's apple snail outbreaks, so a spread of this invasive species under lower water levels and under higher temperatures. So it's a fairly easy assumption that we can make that the future climatic condition and the future water resources condition in the lower Ebro also will have a strong impact on the aquatic ecosystem, as it is very favorable for the invasive species to spread while the endemic species are being pushed back. And so that has in this case, a quite negative contribution to biodiversity. So I said at the beginning that I'm a hydrologist and I model a lot. So there's one study we conducted a couple of years ago in the CLIMB project, a European funded project also, where we were investigating the necessity of applying a different set of available models to see where the uncertainties are. And Enrica Pera was the main driver behind this study. And she was showing for 5 different hydrological models how, on a case study in Sardinia, how different the results can be depending on your choice of model, and how that model reflects terrain features, how the physical processes are represented there, and what the numerical complexities are. And without getting in too much detail, you see there's 5 different models here. I'm just showing one figure of the results. And if you look at the discharge alone for these 5 models, you can easily see that apparently there's lots of uncertainty involved in these types of studies. There's some kind of agreement, but even then you see that some models are not capable of representing properly the annual course of soil water in a semi-arid Mediterranean catchment. Apparently that is due to a lack of understanding of the system, and this lack of understanding is triggered by a lack of information that is currently available to provide on a basin scale. So one conclusion that I would like to draw here is that we need better data to improve our models and to improve our process understanding. So where do we stand? From my current point of view, I would say that we do know, obviously, that climate change contributes to water scarcity in semi-arid regions. There's no doubt about it. It can be felt. The projections are very clear. And I think this will exacerbate strongly in the future. But currently we see there's strong regional variation on the one side, and there's a number of other factors, pollution, for instance, very poor land use or water use management practices that are regionally still dominant. So that is bad news on the one side, but good news on the other, meaning that with a better management approach, we would be able also to overcome certain limitations and provide better efficiency in water usages. We also see that local and regional water managers and water users lack, at least to date, awareness, or they simply ignore the fact of a changing climate. Acknowledging, however, that this is strongly imposing problems on the supply of domestic drinking water, on the conduction of irrigation, of the provisioning of water for hydropower and livestock. So all these kind of things are elementary concerns that will need to be addressed. We also need to acknowledge that data and knowledge gaps in climate and land use change impact on water resources in coastal areas are still very widespread. And many of you will most likely know that despite the fact that we would need a lot of more information, there's currently in many places over the world a decline in observational data, at least those measured in situ and on ground. So I would ask for a research concept that includes an extended and coordinated monitoring program. And what we had proposed earlier, I would like to just show you very quickly. So if, at least from my point of view, if we need to look at coupled water resources models, we should always take an embracing vision. So maybe not only looking at one model, but looking at whatever we have available so that we can run a model ensemble. So we are in a situation where we can do an audit and where we do uncertainty assessment. And in order to drive these models, we can take an approach where we look at land use models that provide some sort of boundary conditions, some drivers for those coupled water resources models. We look at climate model ensembles and assess their uncertainty to get, let's say, a vision of the internal variability of the system and also of the projections into the future. These water resources models, they must be combined with a socioeconomic factor assessment, so we can see where and how those available water resources in coastal areas are in conflict with socioeconomic factors. So that is our baseline to create some sort of risk analysis and modeling. Again, vulnerability and risk assessment are crucial components here to bring this to the attention of stakeholders, to disseminate those findings into a broader public, and this should ultimately lead to better policy, better governance, better management of water resources in coastal areas. But one key point is still missing on this figure, and this is what I would like to highlight and then move over to the other talks in this session. The study site characterization, so wherever we work in such domains, we are really dependent very much on data. And at least from my point of view, this is one critical component where we can use the knowledge of experts in geophysics, for instance, to provide geophysical data, or to use the expertise of specialists in remote sensing, so Earth observation on several scales and several levels to improve parameter retrieval and to assimilate data to improve the understanding of our models. And this is where I would like to stop for this moment and would move on to the second presenter, to David.
Okay, so thank you, Ralph, for this very nice introduction. Indeed, I'm very happy you concluded that data are necessary, and because David and myself are data collectors, and on the other hand, I think data by themselves. Sometimes people say we have to go and collect data as if it was harvesting crops, going out in the field and collect data. This is not exactly the way data should be used. Data collection is the ultimate result of an experiment, of a scientific experiment. So you must have some ideas about how the system is, and you have to collect data to prove or disprove your initial model, to validate the model or to falsify the model. In this respect, modeling and data collection are just the two sides of the same coin, at least in my vision. I don't know if you all agree, maybe there will be some questions later on from the audience. So maybe we can go on with David, and who will be talking about remote sensing data. So data, remote and proximal sensing, I think. So data collected remotely from the ground.
Hello, and thank you for inviting me here today to speak a little bit more on how we can use remote sensing and Earth observations to sort of help out our understanding of how the coast is working, both from a sort of an Earth system standpoint and how that may affect sort of water resources. So thank you, Giorgio, and thank you, Ralph, for including me on this and seeing how all of these sort of pieces fit together. So my name is David Lagomasino. I am from East Carolina University in the United States. My background is in geology. I've done a lot of work in terms of looking at sedimentology along the coast. I've investigated groundwater and surface water interactions using different chemical models. But my primary research is using remote sensing to understand how coastal ecosystems are changing, particularly looking at rates of change and why we see different changes. In particular, I focus a lot on coastal wetlands. And so, you know, these specific environments, mangroves, salt marshes, serve many ecological purposes, providing timber and fuel. They're a source of fisheries and tourism. They help to purify the water, so actually extracting nutrients and contaminants from the water. And in particular, they help to sort of capture sediments as they come off from the rivers and before they go out into the ocean. And also sort of kind of capturing carbon and kind of reinforcing our coastlines. So they sort of allow some energy to happen along the coast in terms of waves and currents without sort of making it highly dynamic. And so they're actually sort of anchoring our coastal our shorelines. But these particular areas where we see these coastal wetlands can also be valuable for other commodities. Here you're looking at a picture taken in Tanzania in the Rufiji Delta. Here was a recent, what we say, slash and burn. And this area is now being converted to rice production. And so again, these sort of coastal areas are valuable not only in terms of their ecosystem services, but that land is also good for different types of commodities. And so we can use different types of satellite imagery to identify certain ecosystem structure and function type measurements to identify these vulnerable areas. Here you're looking at a high resolution commercial satellite image over the Ganges-Brahmaputra Delta in Bangladesh. And you can see the mangrove forest adjacent to the rice agriculture, the rice paddies and the farmers out here. And so this sort of dynamic between humans and the natural system is always changing. And these wetland systems are sort of helping to buffer our more inland ecosystems. In addition to kind of identifying these vulnerable areas, we can actually monitor the sort of rate of deforestation that's occurring in our coastal areas. So here on the left-hand side, I'm showing a Landsat satellite time series over the Sulawesi Island in Indonesia. And what you're seeing here is over this 20-year period between 1994 and 2017, we're seeing this rapid decline in this case, mangrove forest cover as it's being converted, in this case, to shrimp ponds for Indonesia. And this is actually occurring within a marine protected area. And so sort of identifying the balance of protection of these critical areas is important in terms from a monitoring standpoint. And so you can see that the drastic loss between 1996 and 2017. And as Ralph mentioned, we're looking at this land use change. So if you remove your mangrove forest, this buffering capacity that you have along the coast that's keeping the ocean at bay, or keeping it out from the terrestrial areas. What happens when you start to deforest these coastal regions is you're actually bringing the ocean closer to your water resources. And so in this case, the potential for saltwater intrusion into your aquifer, into your freshwater resources, as well as providing any sort of contaminants that are coming out of the shrimp ponds. And so, what we use this satellite information for is not only to sort of make these measurements, but we make sure that we connect with local communities to understand not only sort of the importance of these ecosystems, but how to be able to sort of use these technologies to help inform decisions for their own particular community at the local scale, and scaling that up to a more national level. And so we've looked at using satellite data and millions of sort of satellite images. We've done an analysis to look at what are the causes of changes in these particular coastal areas. And so not only are we just looking at, is this area lost, but actually identifying a reason for that. So here on the left-hand side, in Kalimantan in Indonesia, we see all of this area in green. This is all loss over the last 20 years. And this is occurring primarily because of aquaculture. So that the conversion of these mangrove forests to shrimp ponds. In the Sundarbans in Bangladesh, we actually see a more natural type of loss, so shoreline erosion. So as we have increased wave energy, tropical cyclones, and sea level rise, we start to push back that coastline. So sort of encroaching of the ocean into landward. And in Myanmar, sort of one of the higher countries of coastal loss, we see the transition or land cover transition to rice paddies. So again, these coastal systems serve an important ecological purpose, but also provide a unique environment for commodities that feed the entire world, provide shrimp in the case of Indonesia globally, and rice as well in Myanmar. And so these are just examples of small locations or sort of more local areas, but we've scaled this to the globe and looked at millions of different satellite images to look at this change over the last 16 years. And we can identify sort of where the highest magnitude of this change is happening, both from a natural standpoint in terms of looking at just shoreline erosion, but more of a human-driven component. So these land use changes in terms of changes to commodities. And so from this analysis that we did, we see that over 60% of the losses within these particular areas are driven by humans, with the majority of that being the conversion to commodity type land uses, so shrimp, rice, and oil palm plantations. And so there's a high concentration. And so we're able to sort of identify the higher concentrations of where human impacts are at the sort of global level, providing some more information to countries to inform their particular policy decisions to either one, protect these coastal environments, or two, sort of provide more sustainable management practices for their current commodities. So, providing more sustainable practices for shrimp and rice. So I showed a few examples in terms of these deltas and the land use changes that we see in these deltas in terms of the conversion that we see in these coastal wetlands. And so in addition to those land use changes, there's also the sinking delta problem. And so for many years, and Ralph mentioned this, is the idea of subsidence. So, you add the groundwater extraction, you add loading from urbanization, you add land use change in terms of shrimp and rice, and that starts to the elevation of the land starts to drop. And so again, we see these increase in groundwater resources that's extracting the water beneath the delta. We are decreasing the sediment retention. So there's not sediment coming down because of upstream dams and reservoirs. And as well as we lose those coastal wetlands, we're reducing the ability for the delta to actually hold on to sediment. So more of the sediment is just running off into the ocean rather than being captured and being able to sort of keep pace with rising sea levels. So again, you combine all of these different things together: extreme weather, sea level rise, and economic development, and that adds some additional threats. And so here in a paper published a couple of years ago in Science is kind of showing the vulnerability of these different deltas based off of a number of different stressors. And so one of the things that we can do with remote sensing, particularly when there's access to freely available satellite data, it allows us to do sort of rapid information exchange. And I'm showing here two examples, one from Chittagong, a coastal city in Bangladesh, and one from Semarang, a coastal city in Indonesia. And here what we're doing is we've used Sentinel-1 radar imagery in a particular approach, INSAR, so interferometric radar processing, to look at subsidence in these particular areas. So mention all of the groundwater withdrawal and all of these other issues that are happening along the coast. We can measure that and see how fast these kind of coastal areas are changing. So the areas in red that you see here, these are sinking at a higher rate, and the areas in blue are actually in the opposite direction. So there's more of an uplift in those directions. And so here in the graphs are just sort of looking at specific points in each of these areas. But I do want you to see that this is going up into May and June of 2020. And so again, being able to access free data allows us to provide more up-to-date information that is needed for policy and management type decisions as it relates to water resources. So in addition to that, cloud computing and the ability to do heavy processing within the cloud offers resources to tackle local to global environmental issues. In a study that we've just submitted here here you're looking at Ghana, we're looking at four different land cover changes that have happened over the last 16 years. So changes to vegetation, changes to water, urban expansion that we see, But in particular, what we're focusing on here is gold mining. And so gold mining has exploded in Ghana over the last decade. And this creates a whole bunch of issues in terms of environmental issues because of how they extract the gold from the sediment in the rivers. And so they're using mercury. And so from this, these are illegal gold mining practices. So they're going in, extracting the sediment, adding mercury, and this just gets into the river system. So that not only are you polluting then your river, that can infiltrate into the groundwater, contaminating your groundwater, but then that also goes out to the ocean, where it affects oysters and fish and other sort of substance that is needed for the local communities. And here is just kind of a zoom in on how we're able to sort of identify these gold mining practices, but actually look at it through time. And so we can see that there was this increase up into 2014. And this actually tracks well with the price of gold over the last decade as well. But in more recent years, because the country of Ghana has been working with their local agencies and using more of these satellite data sets, they've been able to do better on the enforcement side and conserve or protect more of these areas. And we've actually measured this decrease in mining. So again, sort of these interactions between what's happening on the land is directly impacting those water resources. And in this case, adding mercury, essentially a poison into the water. And sort of the last thing I want to talk about is the advances in satellite technology that we can measure coastal water depth. And so ESA's Sentinel-2 satellite that launched back in 2015, and NASA's new ICET-2 satellite, which is able to measure both the water surface and the seafloor at a very high resolution. And so this is a new capability that we haven't really had before in space. And so being able to combine both the ICET-2 data, so sort of water depth and water surface, with Sentinel-2, we're able to actually get at water depth at a large area. And so here I'm showing you, how we can use these two satellites to develop new methods to map bathymetry, not only of the coastal areas, but of lakes, of reservoirs, of rivers. And so here kind of showing you three particular case studies in Bermuda, Florida in the United States, and Crete and Greece, where we've been able to map solely from satellite data the bathymetry of each of these different areas. And so being able to measure sort of the reef complex here in Bermuda, the tidal channels, here in Florida, and as well as the shallow slope of Crete, we're able to do this on a regular basis now. And so when there's a disturbance or there's changes, we can actually go out and collect the satellite data again, reprocess our models. And so we actually have then a change in water depth or a change in bathymetry. And so here I'm showing for coastal waters, but we can do this for lakes and for rivers. As long as it's clear water conditions, we can measure it pretty accurately within less than a meter. So the future here in terms of monitoring our coast and water resources is sensor fusion and interdisciplinary collaboration. There is no perfect satellite sensor. There is no perfect Earth observation. Different satellites have their unique capabilities that specifically measure certain components of the Earth's surface. when we combine these types of information in the right way, these different observations, we can address these water-related challenges. So combining, aspects of water depth or land use change, we can really start to get a better handle and better understanding, as Ralph was alluding to, of what's happening along our coast. It's important that there is open and free satellite data and processing platforms that provide access to communities, particularly in these data poor regions, as well as having access to this data will help to reduce the lag time of meaningful information. So, meaning there that if we can get data in the hands in our hands sooner, we can provide better information for policy decisions and more up-to-date information rather than having to wait 5 years for the next model to come out. Remote sensing provides a local to global scale observation that have direct action on protecting freshwater resources and coastal habitats. However, to make sure that's a meaningful response to meet these challenges, we need the input from not only scientists, but policymakers, and most importantly, the community. And so working with the community in each of these different areas, not only sort of provides the engagement, but provides information back to help improve the models that go into this. Thank you.
Thank you, David. I think you listening to your presentation, and also, first of all, I learned something I didn't know. That it is the new satellite capabilities of measuring water depth, and it's actually it is a nice bridge towards what I will be presenting. And I would encourage also the audience to appreciate that sometimes different communities have different jargons, and traditionally remote sensing seems to be on its own, and geophysics is another story. But we're talking about physical sensors in all cases. Of course, in terms of remote sensing, in most cases you use, well, in all cases I would say, use electromagnetic waves, the entire spectrum, which has a lot of advantages and also some disadvantages. One is that you can hardly see anything below ground, and actually seeing the water depth is a step forward in that respect. But if you look at what is happening on the solid ground, there's still a big jump to be made, and it's probably a jump that will never be made properly. And so this is it's actually pretty obvious for me now to present geophysical methods as in continuation with what David has just presented. So maybe we can start the presentation. Okay, first of all, let me acknowledge also help from two colleagues, Andy Binley from Lancaster University and Luigi Tosi from CNR, who helped me put together particularly the examples here. And I will be a little bit, maybe a bit longer than my colleagues, but I'm not sure I will be, because I'm not sure if this works. Okay, yeah. Yeah, if you don't turn it on, it's very difficult for it to work. The first thing is that I would like to give a brief introduction to what is geophysics and what is similar to geophysics in other areas, in other, maybe more closer to everybody's experience. What you see here is a CT scan. I'm not breaking any privacy law because this is actually my body, so I'm not showing anybody else's body. And what you can see here is a couple of kidneys and the kidney stone. The resolution is a couple of millimeters, Actually, the stone is a couple of millimeters. The resolution is 200 microns. And it's actually very nice, from my point of view, that they could see the stone without cutting myself in half, okay? And the principle is fairly obvious, maybe it's accepted by everybody that you can have these kind of images, but it's not obvious how these things are actually collected. And the idea is to run physical measurements from outside the body, and then on the basis of this collected information, reproduce the interior of the body as if you could actually see it. Seeing is a physical process, right? We use electromagnetic waves in a certain range of wavelengths because they actually scattered back by the surfaces. So we can't see through, but we see the diffractions. In this case, we use X-ray to produce an image that then we can read with our eyes and then with our brain. And the results are very useful. Sometimes they may be a bit disappointing, but nevertheless, truth is always knowing the truth is an advantage. And let me also put this kind of information into a wider context, because I strongly believe that collecting data is not, as I said before, is not harvesting, is a really feeding the building of a conceptual model. It is a scientific process where you actually conceptualize the system, collect the data, and then revise the model, and so on. And so let me acknowledge this fairly well-known colleague of mine from the University of Padua, which actually developed these ideas some time ago. More specifically, in terms of geophysical exploration, we tend to use sensors at the ground surface, physical sensors. These collect physical data, but these physical data by themselves can only produce maps. In this sense, they're similar to what you would collect from remote sensing. The step forward is that we know the process that is producing this data at the surface on the basis of the distribution of physical parameters in the subsurface. So there is some physics behind. And using this physics, we can produce images similar to those CT scans. Actually, conceptually, exactly what they do in CT scans. Then, of course, there is a whole lot of things to be done because we need to know what the purpose is. As David said, satellites are very different, right? You can get different information from different satellites. And if you don't know what the problem is, looking at the images is probably useless. You have to choose the right sensors, the right methods. And the interaction with the end user is essential. It's essential there. It is essential also when we try to look at what is happening below ground. So it is a fairly expensive process in terms of energy, not in terms of money, but in terms of energy, because there must be some mutual understanding between who is actually providing the data, who is running the model in terms of process modeling, and ultimately who the end users are. And also geophysical methods are different, the applications are also different, so I don't want to get very much into the details. So I will go to the methods that are more useful for coastal areas, of course. But let me point out a few things. One is that the measurement must be informative. I know this is trivial, right? It seems to be trivial. But actually, when you run measurement at the ground surface, you must know what you want to see. And you must use the right method in terms of the physical properties of the subsurface that will answer your practical question. This is not always the case. Second, you must have a method that goes deep enough and with enough resolution, spatial resolution, to answer the question you want to answer. Everything else is less important than those 2 points. One of the areas where geophysics has been used more and more in the past few years is hydrology. And Ralph introduced hydrology. I don't need to introduce hydrology here again. But there is a set of techniques that go under the buzzword of hydrogeophysical techniques that are specifically aimed at highlighting the processes of hydrology using non-invasive methods. So I will also call geophysical methods non-invasive methods, because they actually hardly get into the ground physically. They're not non-destructive, right? Of course, sometimes you have to put something on the ground, but this is a non-invasive method in a very broad sense. Each method is actually some physical processes that are that actually cause the signal. And in particular, there are many methods that depend on electromagnetic processes and properties. So electrical conductivity, dielectric properties, magnetic properties. And these happen to be the ones that are more useful in hydrology, because the electrical properties of water are extremely peculiar, because water is a polar molecule. So it alters the electrical properties of the ground in a way that geophysical methods based on electrical properties see water very well. In general, geophysical methods can help define three aspects of the subsurface. One is the structure. This is the most classical approach. We want to see what is the structure underground, the geological structure. This is the one that has been used most often in the past, for instance, in mining exploration or energy exploration, petroleum exploration. But actually, if you run time-lapse measurements, very similar to what David has shown in terms of satellite images, if you measure with the same configuration over time, you can see changes, and changes are often due to the movement, to the changes in state that is an effect of movement of water. And so hydrology can often be seen in terms of time-lapse geophysical measurements. In addition, you can also see effects of contamination. And in the context of this session, it is relatively, actually fairly easy to see seawater, freshwater interactions and seawater intrusion, because seawater is much more electrically conductive than freshwater. And I will show you very briefly a few examples. So we end up having some techniques that are extremely effective in this context. And they can be basically classified in two groups. One is electromagnetic methods, which is generally electromagnetic induction methods. And the other is DC resistivity methods. So methods based on galvanic contact with the ground and with tomographic approaches. Let me show you some examples. Okay, this is a coastal area in Sardinia. We are very close to Cagliari, to the main city in Sardinia, and this is an experiment to show that it is possible to see in a hypersaline aquifer. We're talking about an aquifer that has nearly 200 grams per liter NaCl concentration, because this is an aquifer that is lying below ancient salt works since Roman times. And we injected a bulb of fresh water, and you can see in the red is the saline water, the blue is the bulb of fresh water that is evolving over time. Okay, and we used borehole electrodes in a 3D configuration. So we have the capability of seeing changes in terms of electrical conductivity changes that actually represent changes in water salinity, even in this very, very hostile environment. On the other hand, well, okay, let me go back to here. Here we have electrodes that are placed in the ground, in contact with the ground. You get extremely high resolution, but it is not a very fast method. At the other end of the spectrum is electromagnetic induction methods. So it's something similar to metal detectors, okay? You don't need a contact. You just have a signal that is produced, and you get the response of conductors that is measured. And what you see here on the left is an example of fairly large-scale mapping, ground-based mapping of an area in the southern Veneto region, where we collected data in multi-component, multi-coil arrangement. So we have enough information to produce three-dimensional reconstruction of the subsurface. In this case, it is a paleo meander that has been filled, of course, by finer sediments, by coarser sediments, and then you produce the model, the conceptual model of the structure based on this data. Of course, you also need some, or it's better if you also have some ground truthing, so you also have some direct measurements in terms of boreholes, but very few. The boreholes are just placed where needed, okay? I want to show you some other examples that are more specifically related to seawater, groundwater interactions. And I will start with a very simple one. This is in Denmark. It's a coastal area in Denmark where my colleagues wanted to see the interaction between groundwater and seawater in terms of groundwater discharge into the sea. And this has been done using electromagnetic methods, in this case on a small boat, of course with GPS positioning. You see a few transects perpendicular to the coast. We're talking about a fairly small scale. Here you see the scale is a few hundred meters. And, okay, with a certain number of measurements. And basically you see electrical conductivity measured by the equipment that is fairly constant as you are away from the coast, and then the electrical conductivity drops close to the coast. Because, of course, you have mixing between fresh water and saline water close to the coast. In this image, in these three images, you don't see much difference, right? Because you only have singular points along the coast. And even if you map, you see the polygon on the top of the image. Even if you map, you realize that you have a localized area of relative fresh water close to the coast. The actual information is retrieved when you go along the coast. These are two lines. The one is 16 meters from the shoreline. The other one is 10 meters from the shoreline. And the red curve shows clearly where fresh water is actually groundwater, ground fresh water is getting into the sea in a very localized manner, because these systems, like all natural systems, are very heterogeneous. And so you end up reconstructing, again, a conceptual model of the system where you have local places where groundwater is discharging into the sea. I will show you now a similar example, but just opposite. Here we are in the southern part of the Venice Lagoon, where there is a problem with seawater intrusion. And seawater intrusion is not much coming from the lagoon itself or from the sea, it's actually coming from the rivers, okay? These are three rivers, actually two rivers and the canal, which are artificial. They were actually built there by the Venetians in the 1500s. And during summer, when you have like low freshwater discharge, seawater encroaches into those canals, and from there into the subsurface. So you have the infiltration from the riverbeds into an area which is lowland, recently reclaimed in the 1930s, and so it is below sea level. So mapping this is interesting in terms of groundwater, in terms of agricultural production. Here you see a map produced by, again, an electroconductivity meter, which is actually the one in the picture. The scale here is again, a few hundred meters, but the measurements can be run very quickly. The interesting aspect is that here you have images at different apparent depths. The interesting aspect is that then you can optimize sampling on the basis of changes that you see in these maps. So direct soil sampling. So this is an example of optimization. So you reduce the number of sampling and you get the information about the actual salt content in the ground directed by non-invasive methods. Basically, these measurements are run in half a day, okay? As I mentioned, some of the most interesting information comes from time-lapse measurements. This is also an example in the same area, another research group. They basically measured over time. You see different November, February, April, and so on. And these are electrical resistivity tomography images from the surface. So in terms of physical properties, these are electrical properties. In terms of reconstruction, this is similar to a CT scan. And you can see the changes in the season. In July, for instance, you have more fresh water, the red part, it is deeper, and you have less saline water coming from, the saline water is coming, is less extensive, okay? These are interesting, very interesting images, because if you want to model the system, and if you want to use the model for prediction and for management and for policy making, you need this information to calibrate the model. Another way you can do it is also in the same area. They went with floating electrodes on the canals, and you can reconstruct the contact between saline, relatively fresh water in the river, and more saline groundwater, down to a depth, as you can see, of 12 meters below the stage of the river. So there are many possibilities. One of the most interesting, and this is the last one I will be talking about, is conducting airborne geophysics. This is not a new concept. It's been used. It's used also in the mining industry in large areas, for instance, in Australia. The interesting aspect here is that you can see a helicopter that is going around with a big antenna. You can cover large areas in very, very little time. And you have lesser resolution, but you can produce maps that are particularly interesting in terms of management of the coastal areas. One example is again from the same region. It is the southern part of the Venice Lagoon, and without getting much into the details, here you can see red is fresh water, blue is saline water. There are two aspects. One is that saline water is actually encroaching into the land, but also as you go down to like 100 meters, you realize that there is a lot of fresh water below the sea. The northern Adriatic Sea has a lot of fresh water, just a few tens of meters below the surface. And probably these aquifers are extending from here in Trieste all the way to the Venetian coast. We don't know, because these kind of explorations have not been conducted at this large scale. But you can clearly see that below the sea, you also have a lot of fresh water, which is a resource, by the way. And also you can join this information with other information from geophysics, from, in this case, seismic methods, to identify discontinuities, like a clay layer that is actually, of course, changing the possibilities of seawater, of mixing with the deeper fresh water. And you can produce maps. Here you see the maps, say the very shallow map, and then tens of meters down to 100 meters. And you see different processes at different scales, at different depths. So if you have this information, you know how the system works. If you don't have this information, you don't know how the system works. And the system works in terms of the natural heterogeneities of the system in the subsurface. I will just briefly show an example that is not ours, and but is using the same method. This is actually the Monterey Bay in California. It's just published last month in geophysics. And these are similar maps, okay? You can see exactly the same method flying over many kilometers. We're talking about many kilometers here. The scale is 10 by 10 kilometers. And from here, you estimate the thickness of freshwater bodies in an area that is heavily affected by seawater intrusion. So the possibilities are many. Okay, thank you. These are my colleagues, Andy Binley on the top right and Luigi Tosi on the bottom. And thank you. Okay, I think we have successfully managed to get to 20 minutes to the end of the session. And I think I speak also for my colleagues, for Ralph and David, but I think we all would be happy to get questions from the audience here or online. There are clearly many. We threw a lot of ideas on the table, but I think there's clearly a common line that we follow, which is modeling is essential for prediction, and prediction is essential for policy making and enforcement. But modeling is based on data, and data are to be collected based on what you want to see, okay? Not just because you have satellite images and you have nice colors like the ones that David has on his back, okay? Because colors, I mean, geophysics can produce colors, remote sensing can produce colors, even models can produce colors. You know, we all produce images with color images, but they must mean something in terms of the ultimate user, and must be communicated to the policymakers and then to the communities. And after years and years of experience, I can tell you this is not an easy task. It's not an easy task to communicate the meaning of the data and the meaning of the models, or the model results. I don't know if, Ralph, you want to wrap up briefly, because...
Yes, yes, thank you, Giorgio. Maybe just a few words. So I found the two talks of yours, so David and Giorgio, very inspiring, highlighting some of the aspects that we have been looking into for some time, but we see the new potential coming in. I agree very much with Giorgio that especially what you said at the very end, that feeding the science policy interface and getting access, I mean, more immediate and more efficient access to policymakers will remain an issue. From my point of view, that is something that we have been working on for a long time, and it's not a problem of ill will from anyone. I think that there's huge interest on the practitioner side, on the policymaker side. There's huge effort on the scientist side to provide information that is necessary to come to better decision making, maybe more forward-looking, maybe more long-term planning. But this is where I think there's still a lot to be done, and I believe that probably we need a new generation of science communicators that help us to get that interface make it a more efficient interface. Maybe coming back to this slide that I was using, and I will come to one of David's slides that he was using for a summary. Well, we've been talking a little bit in this session about the modeling of coastal areas. Of course, that was only a glimpse of what is already existing. And if we look at this figure, we can see, and what I was arguing for, is that we require coupled models. We have been making expertise in trying to couple surface hydrology and subsurface hydrology models with decent success, I would say, but not to an extent where we can actually claim that this problem is solved or easily solved. It depends very much on the regional aspects. It depends very much on the in situ situation with data that we can have. I can only repeat what Giorgio was saying, that it's not only about collecting data to have data, it is about the best use of such information, that we need to parameterize a model, that we need to calibrate, maybe to validate, most of all, our assumptions. So to see whether our hypotheses that we have with regard to climate change, land use change, urban sprawl, impact on drinking water and irrigation water from coastal aquifers are correct or not. So there is still a lot to learn, and considering that most of the relevant information on aquifers is not easy to get, in particular, not from the ground. We need to have geophysical measurements. We need to make proper use of what David was showing very nicely, the capabilities that we can explore now with novel sensor fusion technologies, using remote sensing imagery from different sensors in a meaningful way to monitor subsidence, for instance, to monitor bathymetry. So this is something that was not really on the page of scientists several years ago, but now with the sensor fusion technologies that we have, we may enter this ground in a more operational kind of fashion. And the geophysical methods that Georgia was explaining, I think they are more than relevant. They're absolutely necessary to include for a sound coupling of modeling approaches. I believe that without those modeling approaches, it's very hard to make sophisticated planning. I believe that scenario or ensembles of scenarios that we can use in a model as digital twins of a reality are key to the success of a forward-looking management of water resources in coastal areas. But we need to work on many levels. So we need to provide a solid upper boundary condition for a groundwater model, for instance, to closely monitor the interaction of seawater and freshwater. We must use the geophysical methods that Georgia was explaining to characterize the subsurface in a more accurate way. And we can explore the capacities of remote sensing, as David was showing, to monitor change in land use, to monitor subsidence, so topographical movement, which I think is a very important component to better understand the subsurface system near the coast. And that always brings me to the, I don't know if it's a conclusion, but it is something that has been discussed in over the past years, I believe, and it's going through a renaissance now. Most of the listeners will certainly be aware of the renaissance of artificial intelligence, now that we have the computational power to do that on a very operational scale. AI has again become kind of the master word to solve all the problems. While I personally believe that is not the case, and it's also maybe has to be stated that what we currently describe as artificial intelligence has had several names in the past, and only now we can maybe explore that better, given the computers that we have for now. I would opt for a pathway that tries to include more of a data-driven modeling in combination with process-based and spatially explicit models that can be fed with remote sensing data, that can be fed with geophysical ground observations and subsurface observations, to try and improve what we currently have. And so for the sake of improving our knowledge and making it maybe also more explainable, I would believe that trying to strive for explainable artificial intelligence as one key element to help us to better understand subsurface systems near coastal zones, that should be a target of research in the coming years, maybe. And at the same time, I'm coming back to the comment that Georgia made before, I would advocate to try and have more professional science communication on board to make sure that the transfer of research knowledge finds its way in a meaningful, in an efficient, and in an explainable way towards sound decision making for water resources management in coastal areas. And I'm moving to this very last slide again. This is what David was using before to illustrate the case. It is a very good reminder, I believe, of why we should worry and why we should care about coastal zones. You see on the top line only a glimpse of all the so-called ecosystem services that coastal zones are ready to provide. And if we take that into consideration, how and why it is worthwhile trying to better understand the freshwater-seawater interactions in coastal zones, I think this is a very good illustration for that purpose.
Yeah,
so thank you very much.
Yeah, Ralph, I agree also on your last comments in the sense that these systems are particularly complex and they have a lot of feedbacks, and sometimes they have unpredictable feedbacks, which are anyway based on physical processes, biological processes, and so on. That's why I also agree with you about machine learning. As you probably know now, it's called machine learning, but it's the same thing, right? It's artificial intelligence.
Deep learning now.
Yeah, yeah. The problem is who is teaching the machine, but because, okay, it's only looking at correlations. We have a question from the audience, from the physical audience, I guess, over there. If you can maybe walk to the microphone and introduce yourself.
It's very strange to be here in this almost empty room, but it's okay. My name is Francesco Chiocci. I'm a marine geologist. I work at University of Rome. So it's, as all of you have said, it's an extremely interesting and important topics. And there are many aspects that are of interest. I have a couple of questions for the two last speech. One is about the remote sensing. Is about the freshwater outflow. It's, of course, the satellite images, you didn't touch this point that was touched instead in the geophysical method. But do you think that increasing spatial resolution or increasing the multispectral capabilities of satellite, it will be possible to have a better definition of the freshwater outflow in the coastal areas? Because it is a very important and often not enough considerate process in some kind of coast. And then for the geophysical methods, in theory, saltwater, freshwater is the most easy thing to subdivide, because one is cold, the other is warm, one is salty, the other is not salty. But then in theory, they mix in a very complex environment like the coastal environment. So one thing is the stratigraphy in the coastal environment, how how technology is advancing in depicting the stratigraphy in the land-to-sea connection. That is always a big issue from one side. And then from the other side is it is possible to quantify the amount of freshwater outflow. Again, you show a good example from Denmark. It is possible to have some sort of water truthing, I don't know, the ground truthing of this outflow. And then the final comment is in between the two. So can the satellite give you the time-lapse evolution and the main event, and then the geophysical methods can go on the ground to maybe quantify and better define the methods? Okay, thank you.
Thank you for the question. Maybe David, you can start answering. We only have 7 minutes before we go offline, so we have to be quick, just give quick answers.
Right. And so in terms of remote sensing and trying to identify these areas of discharge at the coast, I think that the technology and the spatial resolution of these different satellites is just not quite there yet. In terms of being able to capture groundwater discharge, I think the more direct measurement would be changes in temperature, being able to sort of identify, these small scale changes, but sensor resolution plays a big role in that. And the sensors that we have just are too coarse at the moment. This is room for improvement, right? The technology is always advancing. And I think that's where, in terms of, there's trade-offs with spatial resolution and temporal resolution. And so those are things that need to be improved on. But it's a potential to get there, particularly when we could measure changes in temperature.
coming to the geophysical questions. Okay, stratigraphy. I showed an example that is actually just published on remote sensing, just accidentally. That is actually bringing together information from remote sensing to sedimentary cores through geophysical inversion. And I think it's a good example of how you can go from the larger scale to the smaller scale and go more and more into the ground truthing. Because you start from a large images, you direct the geophysical investigations, and the geophysical investigations see below the ground, and they direct the direct investigations. So you only need a few cores to identify the different zones, and then you get the ground truthing that is actually also bringing back truth to the entire process and to the entire data set. I think that that's the way to go. I believe that the future shall go in this direction. I'm not sure it will go in this direction. I have a lot of experience on contaminated sites, and what happens on contaminated sites is that they drill a few holes, they don't understand what the processes are, and when they are really desperate, they call a geophysicist. And then the geophysicist is saying, generally says, okay, you should have drilled holes here and there. You drill all the holes in the wrong place. How? We don't have any money to drill more holes. You know? This is exactly the opposite process that is done in the oil industry, where money counts. They first do the geophysical measurements and then they drill the holes where they expect to get some results. I think that's the right approach. Use the cheapest and also the most effective method to produce large-scale images, three-dimensional images, even four-dimensional images, and then go to ground truthing. So when you ask if it is possible to quantify the fluxes, is difficult because remote sensing and geophysical methods can be time-lapse, but they see changes in the state of the system. They don't see the fluxes, the processes that produce the changes. So you have to somehow to go back from there. And also you can have the systems that look exactly the same over time because they have a dynamic equilibrium. So you have a steady discharge. But if you come to the example in Denmark, once you know where the discharge is, you can go and measure with traditional methods, with direct fluxing methods. Because you know where the discharges are, you know the extent of the discharge areas. Otherwise, you would just go blindly and just measure whatever. So it's always the same process, it's actually the principle of parsimony. You know, start from the simple approach and then go and focus more as needed. I don't know if, Ralph, you have more comments on this, but... Okay, is there any other question from here or from all over the world? We have 2 minutes, but we actually hit 10 o'clock, so I think we can, to stay on time, I think we can close the session here. It has been, as my colleague from Rome said, it has been a very strange experience, but well, we're getting used to virtual reality anyway, so we're going to do it more and more in the near future. Okay, thank you all, and thank you the speakers, and thank you the organization.
Thank you.